Welcome students to the topic on current uses of computing. Here myself Dr. C. SIVA from the Department of Physics and Nanotechnology SRM Institute of Science and Technology Chennai. In this we will actually discuss about the current uses of current uses of optical computing. See, current use of optics for computing. We are in the era of daily explosions in the development of optics and optical components. Several optical components are actually keep on evolving. One good example is actually the camera, which was very bigger in size and now it is actually gone reduced into very small in size, which says the possibilities which are actually available in the optical systems. And they do so many operations. The business of photonics is actually booming in industries and universities worldwide. The data traffic is growing every day by day over the worldwide at a rate of 100% per year. While the US data traffic is expected to increase 300% annually. Worldwide, it is 100%. US alone, 300%. The requirement for high data rate transfer equipment is also expected to continue increasing drastically. High data rate transfer equipments we need. Whatever the way are sending, it need to actually the device have to actually send and receive process very fastly. That kind of devices we need to actually improve. We need to concentrate on the in research aspects also. Let's see electronic switching, which limits the network speeds to about 50 gigabytes per second. Terabit speeds are actually in need to accommodate the growth rate of the internet and the increasing demand for bandwidth, the intensive data streams. To overcome this, the limitations which is being given here and also the advantage, the requirement which is mentioned here is actually focusing on or showing a light only on the optical computing, because optical computing is actually doing eliminating the disadvantages mentioned here and doing the highlighting factor, which is a requirement like 1 terabit speeds can be actually achieved with the optical devices. Most of the components that are currently very much in demand are opto electrical or electro optical based. These hybrid components are limited by the speed of their electronic parts. These hybrid components are limited by means of the speed of their electronic parts. All optical components will have advantages over the electro-optical hybrid components. Unfortunately, there is an absence of known efficient nonlinear optical materials that can respond to low power levels. There is an absence of known efficient NLO materials that can respond to low power levels. Most all optical components require a high level of laser power to function as required. A group of researchers from the University of South California, they jointly worked with a team from the University of California, Los Angeles, Southern California to the Los Angeles, California. Okay. They have developed an organic polymer which can actually switch its frequency in terms of 60 gigahertz. This is 3 times faster than the current industry standard, which is being provided by the lithium niobate crystal based devices. The California team had actually has been working to incorporate their material into the working prototype. Development of such a type of devices could actually revolutionize the information superhighway, and speed data processing for optical computing. Another group from Brown University and the IBM Almaden Research Center has used ultra-fast laser pulses to build ultra-fast data storage devices. This group was able to achieve ultra-fast switching down to 100 picoseconds. The results are almost 10 times faster than currently available speed limits. Optoelectronic technologies for optical computers and communication hold promising it holds a promise for transmitting data as short as the space between computer chips. NEC, which is located in Tokyo, Japan, has developed a method for interconnecting circuit boards optically by using VCSEL arrays. Researchers at Osaka University had reported on a method for automatic alignment of a set of optical beams in space with a set of optical fibers. Researchers at NTT from again Tokyo, they have designed an optical backplane with free space optical interconnects using tunable beam deflectors and a mirror. Actually, for this project, they have from this project they have actually achieved nearly 10,000 sorry 1,000 interconnections per printed circuit board with output ranging from 1 to 10 TB per second. Optics has a higher bandwidth capacity over electronics, which enables more information to be carried and data to be processed because electronic communication along wires requires charging of capacitor that depends on length also. In contrast, actually optical signals in optical fibers, optical integrated circuits and free space. They do not have to charge any capacitors and they are therefore faster, much faster. See, another advantage of optical methods over electronic ones for computing is optical data processing can be done much more easier and is less expensive to the electronics devices. Parallelism is the capacity of the system which can actually execute more than one operations simultaneously. Electronic computer architecture in general sequential manner, let's consider, where the instructions are implemented in sequence. Only one by one we used to give the data and they process again one by one. Okay, not in terms of parallel, very easily. This implies that parallelism with electronics is very difficult to construct. Now we have actually simplified, but however, it is difficult to go in terms of several numbers. We are actually achieving like nearly 20, very close to 20, but beyond we cannot actually achieve. It's finding difficulties. Parallelism first appeared in Cray supercomputers in the early 1980s when two processors were used in conjunction with the computer memory to achieve the parallelism and enhance the speed by more than 10 GB per second. It was later realized that more processors were not necessarily to increase computational speeds, but it could it could in fact be a determinantal one. This is due to more processors are actually being used. There is more time lost in communication. On the other hand, using a simple optical design, an array of pixels can be transferred simultaneously in parallel from one point to another point. These are all the further advantages. Again, to appreciate the difference between the both optical and electronic parallelism, one can think about imagining a system of as many as like 1,000 cross 1,000 independent points per millimeter square. Okay, in an image plane. For this to be actually accomplished electrically, a million non-intersecting and properly isolated connections need to be actually obtained. Parallelism, therefore, when actually associated with fast switching speeds, would result in staggering computational speeds. Very scary here. Let's assume, for example, there are only 100 million gates on a chip, much less than what was mentioned earlier. Further, conservatively, assume that each gate operates with a switching time of only 1 nanosecond. See, such a system could actually perform more than 10 to the power 17 bit operation per second, comparing to the gigabits that are terabits per second rates, which electronics are either currently limited or hoping to achieve. You see, 10 to the power 17 being achieved with optical. In other words, computations that might require 100,000 hour, which means 11, more than 11 years, on a conventional computer could require less than 1 hour by an optical one. Since photons are uncharged and they do not interact with each other as readily as electronics, which is very common in electronics. Light beams may pass through one another in full duplex operation, for example, without distorting the information which is carried by them. In case of electronics, loops usually generate noise voltage spikes. Loops can generate the noise whenever the electromagnetic fields been experienced. Further, high frequency or fast switching pulses will cause interference in neighboring wires. Signals in adjacent fibers or in optical integrated channels do not affect one another, nor do they pick up noisy signals. Finally, optical materials possess superior storage density, accessibility over magnetic materials, because these things are actually complex with electrical, because magnetism with electricity we know very well. They are perpendicular to each other in terms of their fields. The field of optical computing is progressing rapidly and it shows many dramatic opportunities for overcoming the limitations prescribed in the earlier slides. For current electronic computers, the process whereby optical devices have been incorporated into many computing systems is already underway. Laser diodes as sources of coherent light have dropped rapidly in price due to mass production. You can understand a CD-ROM disk have been very common in home and office computers. With this, we can actually stop about the current uses of optics in computing. We'll discuss the other topics in next classes. Thank you, students.